Some structures are stronger than others. What use is this to stunt drivers? What strong structures do they use for protection? And what is it that makes things collapse? Things collapse when they can't take the force. What different kinds of force can you think of? There are 4 main kinds of force: push, pull, bend, and twist. Push, pull, bend, twist. With special lighting, you can see what happens when the same forces are applied to a piece of jelly. The coloured bands show the strain in the jelly. The strain doesn't happen only where the force is applied, it goes right through the jelly. Bending causes strain right through the jelly too, and twisting is too much for it. What sort of forces are these? What sort of forces do bridges have to take? And how do you measure them? You can measure the weight of a truck with a weighbridge. Why do you think some bridges have weight limits on them? And where else have you seen weight limits? If you were fishing, you wouldn't want your fishing line to break. How much mass do you think this fishing line will take? How would you measure the pulling force needed to break something? Like a rubber band, for example. Or a carrier bag. If you want to find out what pushing force is needed to make something collapse, you can use a pushing force meter. At what moment do you have to read the scale? You can calibrate any force meter by using standard Newton weights. Suppose you were making clothes pegs. How would you test them? You'd want to make sure they wouldn't break when you pushed the ends apart, and that the clothes wouldn't fall out by mistake. Do you think this is a fair test? How else would you do it? These scientists are making bridges out of spaghetti and other sorts of pasta. If you had to do that, how would you test the strength of the pasta? What forces are going to be put on it? Do you think this is a good way of measuring what pushing force is needed to break macaroni? Macaroni is strong because tubes are strong shapes. Tubes don't break easily. But although tubes are strong, they're even stronger with triangles inside. Triangles are strong shapes. And because they're strong shapes, you can build lots of different things from triangles. What else can you think of that's made of triangles? And where else can you find triangles used to hold things up? How would you test the strength of different shapes? These scientists found that pentagons are puny and that squares are easily squashed. But triangles are tough. Why do you think they can take so much force before they collapse? These scientists wanted to design a bridge. The bridge had to go across this gap and support the flexible track so that an 800-gram car would run across and get to the other side. And the bridge had to be built from the least possible amount of spaghetti. First, they tested the spaghetti with various forces. It can take a small bending force, but a much bigger pulling force. A small pushing force on a long piece of spaghetti makes it bend or buckle. But a piece that's not long enough to bend takes a big pushing force before it breaks. Most of the bridges were made by gluing short pieces of spaghetti into triangle shapes. Suppose you wanted to design a bridge to take a road over a river. Why do you think it might be a good idea to start with models? What would model testing save in terms of time, energy and money? Which of these designs do you think is best? Testing model structures is cheap and useful, but sometimes you have to do a full-scale test on the real thing. Radioactive fuel elements are transported in these white flasks. The radioactive rods go in a steel box which fits inside the flask. Each flask costs £250,000 and has a mass of 50 tons. The steel walls are 35 centimetres thick and the lid is held down by 16 huge bolts. Are the flasks strong enough? Suppose one was involved in a train crash. Would it break open and spill dangerous radioactive material? To find out, they derailed a yellow test flask and drove a train into it at 100 miles an hour. The train suffered a bit, but the flask didn't break open. Materials like stone, brick and concrete are very strong against pushing forces, but weak if they're pulled. That's why these blocks break. When he tries to bend them, it's a pulling force that does the damage. Remember the 4 forces? Push, pull, bend, and twist. When a bar bends, the top edge is squashed by a pushing force, but the bottom is pulled. So where do you think it'll break if you try and bend it? So, bending forces can break stone. When bridges were made from stone, the engineers had to avoid bending forces. Can you work out why they made arches? In an arch, all the forces are pushing forces, and stone is very strong against pushing forces. If you look at old buildings, you often find that the only things left standing are the arches. Like tubes and triangles, arches are strong shapes. Why do you think this groin-vaulted roof has survived so long? This bridge was cast in iron and put up in 1779. In this old barn, the roof is held up by timbers. You can't easily bend timber into arches, but they used triangles to make arch-like shapes. How do you think they joined the timbers together? What sort of joint do you think might be strongest? A mitre joint? A mortise and tenon joint? Or a dovetail? Why do you think things often break at joins? And why do you think joins are important to the strength of structures? Arches are strong shapes, and arched ribs are what we use to protect our heart and lungs. But the brain is protected by a dome. Why do you think domes are strong shapes? Eggshell is weak, easy to break. What will happen to the eggs in this box? Only one gets broken. How strong are eggs? An egg is like two domes joined together. Do you think it will take more pushing force on the side or on the end? And which end do you think is stronger? Why do you think it's so hard to break an egg by squeezing it? Remember, eggshell is weak. Why are eggs so strong? Some animals live inside domes for protection. They don't need any bones inside. These animals have skeletons inside to hold them up. But animals like crabs have an exoskeleton. They have hard domes for protection. There are no bones inside, but the domes go all the way around to keep them safe. Many seashore animals have exoskeletons. This is a mussel. Cut it open and you can see that inside the dome it's soft and unprotected. What other animals can you think of with exoskeletons? And when might people use the same idea? You need protection for lots of different sports. How many can you think of? So, what makes a helmet strong? What is it about the shape of a car that gives it strength? Why did the driver wear arches round her neck? And how else can we use strong shapes to protect things from damage?
Don't miss Quantum this afternoon at 1:10 for all the latest science news, including a report by Andrew Waterworth on the latest challenge to the Big Bang Theory. Stay with us now for Flip Slide Turn.